All right, let's get started. So, the homework number 2 is due today. And it seemed like a few people had a particularly hard time with this one using the superposition approach. So we'll go through it and work it out. Feel free to interrupt, ask questions, as typical. So using superposition means turn off all independent sources, right? Independent, not dependent. All independent sources, and then turn on one independent source at a time, solve for whatever you're trying to solve for, then do it with the other independent sources, turning them on one at a time, solve what you want to, and then at the end, add them all up. That's it. So for this problem, let's go ahead and start off by turning off the 1-volt source. Turning off a 1-volt source means you replace it with the equivalent internal impedance, which is a short, open, a 1-volt source. 1-volt source should be replaced by a short. Good. I wasn't trying to, I was just making sure because other people said open. That's why I was, just wanted to check. So 5K, 7K, minus to plus 0.2 IX. This is the controlling variable for IX. 2K and 2 ohm. Okay. So we'll start by defining this node V1 and node V2. Everybody okay with that so far? And then we'll just start assuming directions. And again, it doesn't matter what the directions you assume. You just literally start drawing it and go from there. Except for all the power supplies, because they tell you enough information, or hopefully enough information, that you can go ahead and get it. So let's start with V1. So we don't see any current into the node. We only see current out of the node. So we have V1 over 5K plus V1 over 7K. And to solve for the current out of this node, we can't, right? Because we have no way of determining what the current is for a voltage source. So what we're going to do is we're just going to go ahead and replace that dependent source temporarily with a short circuit, or again, the internal equivalent impedance. And then we'll continue on just doing nodal analysis for V2. So that's current out of the node.
Paul,
Yes,
what if you treated that as a supernode?
I am.
Okay,
That's what that is.
okay,
When we replace it with a short circuit, that essentially is calling it, or doing supernode, without formally calling it supernode. All right. So here's the problem. With two nodal equations that we're supposed to write, we just combine them into one, which means we only have one equation. So our second equation needs to be V2 minus V1 equals 0.2 IX. Uh-oh, we introduced a new variable. We would prefer not to do that, but we have to because that's what the power supply is. So all we need to do is one additional equation, IX equals V1 over 7K. Now we have 3 equations and 3 unknowns, and we can plug that into a matrix. Do you all want to see that plugged into a matrix? Or do you feel like you can do that?
Maybe don't put it in that button.
Matrix?
Yeah.
Okay. So remember, what we're trying to do is put everything on one side.
I have a question.
Yes, go ahead.
So in the first equation, why do you sort of combine those two together? Like it seems like nodal, but you're just smushing them all together. Is that kind of what supernode is?
Yeah, because how do we get that current flowing through that 0.2 IX source? We have no way of getting it, right? But we know that that current has to be the sum of those currents, right? So what we do is instead of saying that's the current, we just add in this current and that current, and then the residual of that should be equal to the current through the 0.2 IX volt source. Does that answer your question, Matt?
Yeah, thank you.
Yep. Again, you may have been taught super mesh or super node. I don't like to call it that because I think everybody, when I asked you at the beginning of this material, were you exposed to super mesh and super node? And I don't think anybody said yes, we had been exposed to that. So when you do this super mesh, super node, it's like a very formal procedure. And for me, it's like, how do I get this current? Well, I know this current here has to be equal to the sum of those two currents. That's it. I don't care about super mesh, super node. I just know, looking at it, that current has to be the sum of those two currents. Done. Okay. So we have -2 equals plus 0 IX, right? Because we have 3 equations and 3 unknowns. I've got to make sure I have all my variables included in each equation, which means I have 0 IX is in my first row of my first equation. Over here, I have 0 equals V1 minus V2 plus 0.2 IX. And lastly, 0 equals 1 or V1 over 7K plus 0 V2 minus IX. Okay? Yes, sir.
Can you just get rid of that? For the IX, the second equation?
Yes. So for those of you who couldn't hear in TV land, can you get rid of the second equation by plugging the third equation into the second equation? Absolutely. But what was the problem asking for? IX. So by substituting in that equation, I've just lost IX. So then I've got to go back and recalculate what IX is equal to. So I can do that, but it's like, well, the matrix already just it puts it up for me. So there's no advantage to doing that. But yes, you absolutely can. But remember, I'm lazy, so why bother doing extra work if I don't need to? So this is going to be IX because of the 2 amp power supply. Now we have to redo this with the 1 volt source in here. So I put my 1 volt source. I have 5K. I have 7K. My dependent source still lives here. And that hasn't changed. And how do I turn off an ideal current source? Replace it with its internal equivalent impedance, which is an open circuit. So I'm done, right? I don't have to do anything more over here. I'm not even going to bother showing it. I have V1, V2, assume some directions, and I don't know, we'll just assume it this way. Right? Doesn't matter because it'll clean it up when we get negatives or positives at the end. So now I'll do my V1 node. So V1 minus 1 over 5K plus V1 over 7K. Again, I've got a voltage source in there. I can't calculate the current, but I know this current had better be the same as that current, right? Don't need to know about supernode, but I do know that those two currents have to be the same. So that becomes, and that sums to 0. And then I need one more equation, at least one more equation. So V2 minus V1 equals 0.2 IX. Darn it. I keep tripping myself up, right? I keep introducing another variable. So I have to add a third equation. IX equals V1 over 7K. So those last two equations are exactly the same, whether it's done with superposition or not. So if I set this up in standard form, I have 1 over 5K equals V1 times 1 over 5K plus 1 over 7K plus V2 over 2K. And we still need to have 3 equations, 3 unknowns. So I'm going to go ahead and make that 0ix. Equation number 2, nothing on this side. So V1 minus V2 plus 0.2ix, because I just dragged everything to the right-hand side of the equation. And lastly, 0 V1 over 7K, no V2s, minus Ix. And when I'm done, I add the Ix you calculated over here and that Ix over there, and then you get the answer. Questions on that? Did I do a bad job? Did I lose everybody? Or, and again, this is not a judgment, or you're thinking like, oh my God, it wasn't that hard. I can do this. Hopefully what that does, nobody here should be saying like, I can't believe I'm so stupid. I did this the wrong way. It's like, wow, I'm actually pretty good at this stuff because I can see this stuff. It's saying two similar things, but very different, right? One is popping you up, making you feel better about, hey, I can do this stuff. As opposed to the other one, which is like, do I belong here? Like, absolutely you do, because you can see this and like, yeah, it really wasn't that hard. I probably made it harder than I needed to. A lot of that is what, a lot of college is what you do. I have a 10-year-old who's a really good athlete, and a lot of why he suffers in sports is because he doesn't have confidence. It's the same thing in school. Why do you suffer? Because you don't have the confidence. Be confident. Yes, sir.
For both of these equations, how exactly would you get Ix?
Add them together.
Like,
Add the Ix's together. Because we're both assuming that they're going in the down direction. So we just add them up. If we had them flip-flopped, then that would be different. But we have them, the arrows going down. So we're good to go. We just add them up. Yes. Not this one. Oop. Minus 339 milliamps. But you should also have it as well too, because the solutions should be ready to you, I think, when you get out of class. Any questions on any of the other homework? Because a lot of your first test will be this stuff. If you can do this stuff, no problem, you'll have no problem in your first exam. Which we should talk about the first one exam date. My suggestion would be to do it next Friday. Because I think we have enough material covered that we don't want to wait too long, right? You've already had a homework. You're gonna have another study or review session this week on this type of material where Mark will go over some of this stuff. If you wait too long, so if you wait another week, that's gonna be 2 weeks since you'll be covering the material. And for your classmates who are doing both classes, both of my classes, they have an exam on Monday. And so one exam on Friday gives you enough, should be giving you enough of a buffer. It actually gives them, 5 days essentially between the two classes. So that should be enough time to study. But that's my suggestion.
I'm fine too.
Who votes for a week from tomorrow, which is the, I don't know, what day is it? October 1st or 2nd? Who votes for October 2nd? 1, 4, 5, 6, 7, 8. Who votes for, actually,
The second is a Thursday.
okay, the 3rd then.
Yeah.
Let me put up a poll for TV land. I don't know why
And-
these are.
Oops.
Hello?
Shit. Oh.
Arthur, we can hear you talking, so
Oh, sorry.
it's okay. We're happy to hear you talking. I don't think you realized. All right, let's launch this bad boy. Oh, where did it go? Oh, here we go. I don't know why. All right, TV land, you should have a poll. Right now, I think it's 8. Oh, I forgot to ask. Who wants it on 10 10 in the class? It's okay. There's nothing. All right, so whoop. Right now we have 13 for 10-3 and 2 for 10-10. 14. So it looks like a week from tomorrow. So the only last question I have for you is, when do you want to do an exam review? You want to do it on Tuesday? Give you a couple days study time, or would you rather wait till Thursday, right before the tests? Yes. Last time is too precious, right?
Thursday.
So we cover the new material Tuesday and then Thursday would be beginning. And then
Flip flop, whichever one you want. You either do exam review on Tuesday and new material on Thursday,
Okay.
or vice versa.
I would- Yeah.
Review Tuesday, then they give you a couple extra days. Okay. Anybody have an issue with that? Everybody in this class seems to prefer a review on Tuesday. How about
Tuesday's fine.
Yeah, I'll take Tuesday.
Okay.
There's no lab tomorrow, John?
Paul? Yes, there's a study session. So you're not going to be going over new material. You're just going to be going over,
So I'm gonna study on Friday and.
well, tomorrow's not going to be a study session. He's just going to go practice problems. So it's not going to be specific for like going over, like a review is talking about topics, answering questions. Do you understand this? Do you know that? You know, kind of jarring your memory, where tomorrow he's just going to put up a bunch of problems and he's going to work them out. And so it's not really a review. It's more like practice. It's a subtle difference, but it's more of a practice type session tomorrow as opposed to a review. That's the way I look at it. He usually does a Zoom for every class, doesn't he? Every lab. He did not do one last time?
No, he did. I just
did.
wanted to make sure, like, if this one's gonna be a little bit.
Yeah, I think there'll be a live portion, but he also does it with Zoom, kind of like we do in class. And the nice thing is you can rewatch the video if you want. Same thing with these. Okay. Good stuff. You feeling good about yourselves or feeling peaked? I hope you're feeling good about yourself because again, this is all stuff I'm hoping you've already seen. And now it's just like, what's the expression? Polishing a stone, right? So right now we have some parts that are rough. So now hopefully we're just smoothing it out. All right. So let's go back and do some additional circuit elements. And we only have a couple more, right? That we haven't looked at. Our capacitor, but we're going to do it differently now because I don't know what they do at SMCC. But I know at here and at Eastern Maine, they might introduce this as CDVDT and then almost immediately forget you're taking the derivative, right? Because most of the students who take circuit analysis here and at Eastern Maine either haven't had calculus before they take it, or are taking calculus concurrently. So their calculus skills may not be the best. So that's why we actually don't do a lot of stuff with derivatives. But in this class, we will, because it actually helps us if we can do the calculus, and it gives us a deeper understanding of how a capacitor actually works. So here's our capacitor, and it's CdVdt is the equation for I, which may or may not make sense. But if you think about a capacitor, how fast or how slow the discharge of the capacitor is occurring is indicative of current flow, right? So if that capacitor is discharging very rapidly, then the current is quite high. How do you know if a capacitor is discharging very rapidly? You can either measure the current or you can look at the voltage, because capacitors don't store tons and tons of energy. If you see that voltage dropping fairly quickly, then that means that you're getting a lot of current. Or you can be charging it, right? A current capacitor can act as a load or a source, depending on where it is and the timing of, how that capacitor is being used. And everybody knows the units for capacitors are farads. So how much energy does a capacitor store? Capacitor stores joules, right? Doesn't store watts. It stores joules, but the rate of charging or discharging is going to be based on the instantaneous power at any point in time in the capacitor. So that's I times V, both in the time domain. And that's CdVdt, or that's equal to the rate of change, which we know power is just equal to the rate of change of the work. So the energy that's stored in a capacitor is the work. So you integrate dw dt equals that value, and you end up with 1/2 CV squared. That's the amount of energy that is stored. So if you know what the voltage is, you square it, multiply by the capacitance, take 1/2 that, and you've got that answer. Does that equation, 1/2 CV squared, look like anything that you might have seen? To me, it looks a lot like potential energy equation, right? The potential energy of a system, which is, how high a mass is. You've got a lot of potential energy there, right? So that concept of 1/2 CV squared is based very similarly to how we store energy in a physical system. So a couple key things about capacitors, right? Once it's fully charged, that means no more electrons are going into the capacitor. So for all intents and purposes, that capacitor looks like an open circuit. It isn't physically an open circuit, from the perspective of analyzing the circuit, we have no charge in there, which means it's an open circuit. So if we want to simplify a bunch of our circuit analysis, it's usually helpful for us to look at things in time instances, when the capacitor is fully charged or when it just starts charging. So it becomes an open circuit. Also, voltage cannot change instantaneously. Anybody know why it can't change instantaneously? Why can't the voltage on a capacitor change instantaneously? Well, let's take a look at this equation over here, right? So I equals C dV dt. I over C equals dV dt, right? If I integrate that, both sides, with respect to dt, what I have is, I gotta put my dt here. My voltage is equal to the integral of I, 1 over C out front, dt. What do we know about integrals? What is the definition of an integral? Area under a curve, right? So can a voltage that is based on an integral, can you have an instantaneous change in the voltage if you're looking at the area under the curve? You can't, because that would mean that all those electrons got flushed away instantaneously, right? So anytime you're looking at an integral, the system cannot instantaneously change. So just like the voltage in a capacitor, there is no instantaneous change. That's when the concept of it can't jump. You can get tons and tons of current, because I equals c dv dt, and derivatives can be very, very high. But integrals, because you're adding area up or subtracting area up, you can't get those instantaneous changes. And we already talked about caps either absorbing or supplying energy. So, can you find I of t for the voltages shown here? What would be I of t in A? Well, we start off with I of t equals C dv dt, right? So the first thing I do is, what is the slope of that line? 0? There is no slope, right? So what is dv dt? So for this one, I of t equals 2 farad times 0. There's no current there, is there? Which makes sense because my capacitor voltage is fixed. So I'm not putting any electrons in and I'm not taking any electrons out. So that is a fixed voltage, which means no current in, no current out. Over here, is this a sine wave or a cosine wave? Sine wave, right? Because it starts at 0. So if I do my I of t equals my capacitor 2 times the derivative of a sine wave, what do I end up getting? You get a cosine wave, right? So the derivative of sine is cosine. So this is cosine. But what is the sine of t in here? Is that correct? What is the period of the sine wave? Two? Looks to me like it's 2 seconds, right? It repeats after 2 seconds. So my period t is equal to 2 seconds. Was going into my sine wave, is that, do I put 2 seconds in there? I do not, right? What do I put in? Kind of. First thing I have to do is, in the sine wave, right, I have to have a frequency, right? So I'm not taking the derivative of time, I'm taking the derivative of a frequency. So I can get frequency as 1 over the period, which is equal to 1/2. Do I put 1/2 in there? No, I put not hertz, but I put radians per second, right? Inside of the sine wave should be radians per second. So it should be sine of omega t. So 2 times pi times f equals omega, which means that this is equal to pi radians per second. So inside this equation is pi t. So what is the derivative of sine pi t with respect to t? It's cosine of pi t times what? Times pi, right? Am I blowing everybody's mind by doing this stuff? Has it been a minute? Right, because inside the sine wave, it has to be, you're taking the derivative of something that is a degree or a radian, right? So you can't have frequency in there, which has the unit of 1 over hertz. Sorry, hertz, which is 1 over seconds times seconds. That's a derivative of no unit. So it has to be your radians per second. When you multiply by seconds, you get radians. And here's our waveform. Okay. So we got 0 and we got a cosine. And let's just go ahead and rewrite this. So I of t is equal to, what did we say it was? 2 pi cosine of 2 pi, of pi t, sorry. All right, that's the equation. So this starts to tell us a little bit, right? Because our original waveform is a sine wave. Now we have a cosine wave, correct? Well, we can replicate that a cosine wave is really just a sine wave that has been phase shifted by 90 degrees, correct? And just for your own edification, here's what I strongly recommend. You know that this over here is in radians. So you better indicate that that is in degrees, because one of the things students do a lot is they forget. They'll just add pi times t plus 90, and they're wondering, like, why do I get goofy numbers? That's 90 degrees, but it's in degrees. You really should call it pi over 2 to be able to add it to the pi times t term. I don't have any issues with you calling it 90 degrees, because that's what we do in a lot of AC circuit analysis. But to help you identify or differentiate, please call that a degree. Put the little degree symbol, because maybe that'll jar your memory to convert that. All right. 5 minutes. Give me these two. Be careful, right? One is a current and one is a voltage. So be aware of those facts. And while you're doing that, I'm gonna go blow my nose. Sorry, this has been like a 2-week cold. So. One more minute. All right, what you got? Anybody? Nothing? Let's start with the easy one. Let's do voltage. Because we know that I is C dV dt, right? And we got voltage over here, so we're just going to take the derivative. And the derivative, rise over run for a line. You don't have to do anything fancy, just call it rise over run. So dV dt over here, it rises 8 volts. And it runs 2 milliseconds, right? So that's going to be equal to 4 times 10 to the 3. If I get that right? So my current now is equal to 5 mics times 4 times 10 to the 3, which is equal to 20 times 10 to the minus 3. And it's only going to be that current between 0 and 2 milliseconds, right? So my plot should be that I get a constant current from 0 to 2 milliseconds, and the current is going to be 20 milliamps. And then after that, it's 0, right? Because the voltage is not going up or down. It's fixed. So there's no change in voltage. So that's my first one. We'll look at that plot here in a second. My second one's a little bit harder because I've got current. But it's not too much harder because we saw at the beginning of class that V equals 1 over C integral of I of t dt, correct? So in this case, you're integrating the current over time. And this current's pretty easy to integrate, isn't it? It's just a rectangle. So over here, I start with 0. And then when I get to here, how do I solve for the area under the curve? Length times width, right? Width, right? So it's 2 times 20 milliamps equals 40 amp seconds, I guess, whatever. Or milliamp seconds. So now I'm going to go ahead and plug into my equation. And I see at 0, I've got a voltage of 0. And at 2, oh, this is milliseconds, not seconds. So this is here. I have 1 over C, which is 1 over 5 times 10 to the minus 6 times 40 times 10 to the minus 6. These will cancel out. And I'm left with 8 volts. So it starts at 0 and ramps its way up to 8 volts. So this current here will cause that voltage, or the voltage that results is going to cause that current. Does that make sense? Kind of, sort of, maybe. Yep. The last step, or the part A?
You have 2 amps.
Sure. So we know that's not 2 amps. This is at 2 volts, right? So at 2 volts, what I'm trying, or not 2 volts, 2 milliseconds. What I see is my voltage is going to be equal to 1 over C, which is 1 over 5 times 10 to the minus 6. Then I'm going to multiply by the integral. Well, the integral is just the area under the curve, which in this case is a rectangle at 2 milliseconds. So that multiplies by 40 milliseconds. So the units will cancel out. And I'm left with 8 volts at 2 milliseconds. And it ramps up linearly, right? Because as I add this area to this area, it's going up the same amount each time. So it is a linear rise. It isn't an exponential. It is a linear increase to get to that value, or to get to those those specific areas. Yes, ma'am. Right here? Because I just did the slope, right? I did dVdt, which I see it rises 8 volts. And it does that in 2 milliseconds. So 8 divided by 2 milliseconds is 4,000. Okay.
And can you just like explain the 105 times 10
5. Oh, this one we just did right here. So this right here, that's 1 over C, right? It's a 5 microfarad capacitor. So I just plugged in 5 times 10 to the minus 6. That's 5 microfarads. Then I needed to get the area under this curve. So this area right here, I can calculate it using length times width. It's just a rectangle. I don't actually have to do any derivatives. I can just look at it really quickly and say, I know at 2 milliseconds, that rectangle is complete. So the entire area of the rectangle, I can calculate by going length of 2 times the height or the width, whatever you want to say, is 20 milliamps. So 2 milliseconds times 20 milliamps equals 40 milliamp milliseconds. That's the area under the curve. So then I just put that in the equation and I end up with 8 volts.
How does the power? Million second.
Well, this is 10 to the minus 6. So this is times 10 to the minus 10 to the positive minus 3. Sorry. A milliamp is times 10 to the 3 minus 3. And I have another 10 to minus 3. So the minus 6, when I move it up into the numerator, becomes positive 6. So positive 6 times negative 3 times negative 3 becomes 0. So 10 to the 0 is just 1. Okay. Let's do the inductor. So the inductor is different, and where the capacitor stores electrical charge, the inductor works on a very, very different principle. And the principle is based on, it is opposing changes in current. So you will develop a magnetic field as the current is changing. All right, so change the current, you develop a magnetic field. And then that voltage that you get across it is how hard that inductor is either storing energy or dissipating energy to prevent the changing current. So it only stores energy in its magnetic field when the current is trying to change. Once the current is constant, there's no energy being stored. It's there, but there's no additional energy that's being put in. So that becomes LDIDT, which is how you generate a voltage. So one of the things for you for senior projects, you can develop sky-high voltages on these systems just by trying to change the current very rapidly. So like in the case of turning off a power supply, like a MOSFET that's connected to an inductor, you switch it off and that inductor says, I ain't happy with this. So I'm going to generate as high a voltage as I need to, thousands of volts, so that I'll keep that current going. It'll decay very quickly because the magnetic field, the energy in the magnetic field that is stored around it dissipates very quickly, but it has a lot of, if you worked in the utility industry not that long ago, a lot of people were getting killed because they would have these things called current transformers, which are basically big inductors. And they would try to work on these circuits. And so they would pull a wire, which would open circuit the CT or open circuit the inductor. Now, all of a sudden, you went from whatever current that was going in to 0. And so it would arc across the terminals that the electrician was lifting. And so that arcing meant it would either burn the person or cause an electrical shock to the electrician. And then, unfortunately, some of the people passed away. Many years ago, when I was living in Washington, D.C., I went to a nuclear power plant in North Carolina called McGuire, and they were doing this test that it was required for them to de-energize the solenoid valve. it was a DC solenoid valve and it was very unhappy with being de-energized. So what would happen is it would generate a crazy high voltage, so high that it would arc across a set of contacts and start up their main emergency diesel generator. That wasn't supposed to happen. And at a nuclear plant, when things go unexpectedly and they start up, it's like, oh boy, that's really, really bad. And so the root cause was when they were de-energizing the solenoid, they had to be careful. Do you know how they fixed it? You basically put a Zener diode across the terminals. So if the voltage got so high that it started to look like it would arc, it would short out and go back into the solenoid valve. So if you use H bridges, like if you're using MOSFET H bridge to power some sort of a motor to go forward and backward, built into the H bridge are, they're called flyback diodes that actually prevent you from generating sky high voltages that kick back. So if you buy an off-the-shelf item, an H bridge, it almost guarantee will have built-in flyback diodes across them to protect it from generating high voltage, because there's nothing you can do. That MOSFET switches off really quickly, shuts off the current. The motor's really pissed that it did it, so it generates a crazy high voltage and it fries the H bridge. So that's the reason why H bridges come with those flyback diodes built into them. We can double check that too. Let's see. I think all the H bridges come standard with it. These are going to just show. I'm going to show the basic circuits, but here we go. Let's see circuit diagram. Here, H-bridge motor driver circuit. See the motor? And you see the H-bridge. So this is showing it's BJTs, but you will notice you've got D1, D2, D3, and D4 directly across the current terminals of the H-bridge. You don't need the H-bridge for those to conduct, right? It's going to conduct based on turning on those BJTs to get it to go in the forward or the reverse direction. But once you de-energize those BJTs, those flyback diodes are just Zeners. They will operate and short out, and then they'll just send the current back to the motor so that you don't actually fry anything. So that's the thing about inductors. That's why transformers don't work for DC, because if you had fixed current, there's no changing magnetic field. You're not increasing or decreasing the energy stored, so it doesn't work. So you can't energize it. You can energize a transformer DC, but it won't run successfully for a long period of time. Unit for inductance is Henry. Henry, question?
No, I just realized that that's probably why they stick a diode in the bus electrical center on the AC compressor clutch circuit.
Probably, I know a lot of electric, any vehicle, if they have, because they have a DC system, a lot of times they have those built in to provide the protection for those cars, because they blew so many of them, and it's so cheap to put in a Zener, or you can put in what's called a metal oxide varistor. Another term is if it's for a high voltage applications, they call them surge arresters, right? That's all it is. A surge arrestor is basically a power electronic device that conducts when the voltage across it gets too high. So all those systems, they have them built in. But energy stored, 1/2 Li squared. This looks pretty familiar or similar to the capacitor, except this is based on kinetic energy, right? The current is moving. So you only have work being done when you have a current flow. So one is potential energy and one is kinetic energy. So similar, but very, very different. So when you are fixing a DC source to a system with an inductor, because the current is not changing in the inductor, then you're no longer generating a voltage to oppose any change, because it's not changing anymore. So if you're not putting any energy in your inductor, that system looks like a short, not an open. I didn't say goes to zero current. I said no more changing current. So if the current doesn't change, it no longer develops a voltage. No voltage means 0 volts. So you can effectively replace an inductor by a short circuit if the inductor has reached what we would call steady state, it's fully charged. And as we just stated, your current in an inductor can't instantaneously jump. And that's because if I take this equation here and solve for the current, I have I equals 1 over L, integral of V of t dt. Same condition. You cannot get an instantaneous change because you're taking an integral. You're looking at the area. The area cannot change instantaneously in time. All right, I'll give you 5 minutes. Now that we're pros at doing these, right? We're gonna do the same thing for inductors, but remember VL equals L di dt, or I equals 1 over L, the integral of V dt. So show me that you can get to that. Given the current, can you get that voltage? So I'll give you 5 minutes. That's the voltage, yep. I'll clean it up a little bit. One more minute. All right. What do y'all got?
Paul, I have another question.
Yes.
So that I equation, is that more like the change in current?
Right here?
Yeah, because when I when I do the 1 over L times the integral of V, like between like 0 and 2 seconds, it says it's 0 amps, but is that more like a change in current because there's no change in between 0 and 2 seconds?
Correct. So there's no charging happening for the inductor. So
Right.
the current at that point is fixed. It doesn't go down.
You just need the arbitrary constant to make the graph work then, or no?
Yeah, that's right. Because remember, your integral is you can't change the current instantaneously. So that means whatever the current was before the condition of the circuit changed, it has to be the same after. So in this case, you can see it gets up to 1 amp and then it stays at 1 amp. So the circuit it went through some sort of change to keep it at 1 amp and then doesn't move at all until about 3 seconds when it starts to change again. Okay? Does that answer your question, Matt?
Yeah, thank you.
All right, well, let's go ahead and do it. So now I'm going to change it up a little bit and I'm going to start looking at timing intervals. I'm going to look at my current because I got more than one, right? I've got 3. And so I'm going to start to develop a table and I'm going to call it my time table. So from -1 to 0, right? I have one time interval. From 0 to 2, I'm going to have another time interval. From 2 to 3, I can see that it changes. And anything after 3, so I'll just put beyond, it doesn't change. So I actually have 4 time intervals, but really only after the first 3, it kind of sticks the same. So those are my time intervals. Now I am trying to solve for my voltage, which is L di dt. So why not solve for di dt in those time intervals? Right? Because that's like the major driver to solve for the voltage. So I'm going to do di dt first. Once I have that, then I'll actually solve for the current. So I'm not going to multiply it through. I'm just going to solve for the derivative. So the derivative over here, rise over run, it rises 1 and runs 0. Sorry, 1, right? It's not -1, it's 1. So the di dt is 1. The di dt from 0 to 2 is 0 because it doesn't rise at all. For 2 to 3, it rises -1 and it runs 1. So -1. And lastly, that becomes 0, right? Because it's not rising at all. So it's 0. So now I can solve for VL, which is equal to L di dt, which is equal to 3 times 1, 0, minus 3, and 0. That's your first blush, right? You want to go ahead and solve for that. And that's perfectly fine because we see that you can get instantaneous changes in voltage. So I'm at 3 volts, then I go to 0, then I go to minus 3, and then I go to 0. So for plotting that from minus 1 to 0, I go up to 3. Then I go back down to 0 and stay at 0. And I can do that instantaneously because I'm taking the derivative of the current, not the integral. And I run all the way along until I get to 2. My table at 2 tells me I jump down to minus 3. Then I stay flat at minus 3 until I reach 3 seconds. Then I drop back down to 0. And then I stay there until the next event in my circuit happens. So the difference between the capacitor problems and the inductor problems is not that the approach is any different. It's just that this approach, I think, makes it easier to follow. By dividing it up into intervals and then setting up a table, I think you're going to find that it's a little bit easier to do. Because then I can keep adding stuff on. I can add on power, I can add on all types of different things. Let's even add on current here. So this is how I would put my current, not my current, my current over here. I'm going to see from minus 1 to 0. And here's the important thing. I'm going to start off at 0 and then work my way to positive 1. Right? That's what the chart shows. And since I can't have an instantaneous change in current, I know that the start interval or the starting value for the next interval must be equal to 1. Right? I don't even have to look at the graph. I know that my current can instantaneously change. So if I ended at 1, I had better be starting at 1. Then I walk through, because I can go through changes as long as they're not instantaneous, and eventually work my way over to 1 again, right? There's no change in current. So I start at 1 and I end at 1. That's the starting point for the next interval. So if you want, go ahead and just show little arrows showing I have to copy that down there. That has to be the exact same value. So I need that to be the starting point for the next value. Now I'm at 1. And at 3 seconds, I work all the way to 0. And then for my next interval, that's the starting value for 0. And then it goes on until, again, something changes in the circuit. So the difference between the voltage and the current in an inductor is your current can't change instantaneously in the inductor, and the voltage can, but in the capacitor, the voltage can't change instantaneously, but the current can. So you'll see in this column there, you see the arrow showing I'm starting at 0 and working my way up to a number. I don't instantaneously change. Like you'll notice here when I did my voltage, I just multiplied. I just went up and down. So I just did the slope of the line and multiplied. I don't care about instantaneous changes. I can do that no problem. I can't do it for current. Okay? So again, that's just a suggestion of how to do these things. I find laying them out logically, it's really easy to check your work. And then it's also easier to build the table. Anybody do anything like this to try this problem? Again, you don't have to do it this way, but how did you organize how your plot, like what if I said this? If I had said, given this curve and a 3 Henry inductor, find VL of T. Could you have done that? If you lay it out as a table, I think it's a little easier to solve for the voltage. If you just kind of do it haphazardly and don't show intervals, it might be more difficult to do that. So again, that's why I find it much, much easier to lay out the tables, because more often than not, you're not gonna have both curves on the plot. You'll be given one, then you gotta find the other. Okay? Any questions on this? Not something we have to do all that much, but the reason why we're doing it is two reasons. First off, it's giving you hopefully a better understanding of inductors and capacitors and what they are physically trying to do with our circuits. So you can think about for filtering and all that type of stuff. But I'm also teaching you a little bit of sneaky math, aren't I? Didn't we just say that derivatives are slope of the line? I didn't actually do the derivative of x squared plus 3x plus 7. I just said this is our rectangle. So what is the area under the curve? What is the area under the curve, or what is the slope of the line? I actually don't need you to do derivatives and integrals. I'm just trying to give you a good fundamental understanding of what integrals and derivatives are. Because calculus, if you think about it, is all based on real world physical systems. So to truly understand what's happening in the real world, you need to understand what the calculus is, right? That's why we have to do it. All right. If things ramp up 10 times faster, so what that means is that the slope of the lines are higher. So instead of taking 1 second to go from 0 to 1, I do it in a tenth of a second. Then your voltage just goes to 30 volts. So remember what I was talking about, like generating some crazy high voltages? You can do those with buck boost converters. If you want to build an analog buck boost converter, you can see I was at 3 volts. Now I'm going up to 30 volts. And all I did was shorten the time for how that current had to spike up. And if you shorten it and shorten it and shorten it, you can get some really high voltage spikes in your system. Excuse me. How do we show that inductors in series work the way that we expect them to do? How do inductors in series add, by the way? Do you know? Same as resistors? Can you show me that? Can you prove it? Remember what your teachers did back in the day, right? They probably just waved their hands and said, well, inductors, they waved. Some teachers might have said, hey, an inductor is just a coil of wire wrapped around something magnetic. And if I have another coil of wire wrapped around something magnetic, can't I just take that coil and just make it longer? So it's like adding them in series. That kind of makes sense, but it's not a great analogy. So let's do an easier one. So remember our equation for voltage? That's L di dt. So V1 equals L1 di dt. V2 equals L2 di dt, and on and on and on. We'll just start off with 2 and then we'll go from there. So we'll say that V source equals V1 plus V2 with just our 2 inductors in the circuit. So that's L1 di dt plus L2 di dt. What do you know about di dt? Is it constant? It's taking the derivative of the current, so you are getting a slope, yeah. But what do we know about di dt? Aren't these the same? Because I is the same. The same current is going through both inductors, right? So because that's the same current, the di dt is going to be the same. So I can actually write this as L1 plus L2 times di dt, right? Because it's the same value of current. And if I want to place that one, if I want to place all those resistors as one equivalent, we know that V source has to equal L equivalent times di dt, right? It should be exactly the same equation. And so what that tells me is L1 plus L2 has to be equal to L equivalent to make that system work. If they weren't, then they wouldn't be equivalent to each other. So inductors in series add just like resistors in series. Whether you do that in the time domain or steady state domain, it doesn't matter. They add exactly the same. What about in parallel? We'll do one more in parallel and we'll call it good. Let's say I have two inductors here. L1, L2. I source. What do we know? Well, the current through here, what's the current equal to? IL2 is equal to 1 over L2 times the integral. Oh, no, not the integral. Yeah, it's the integral, sorry, of V of t dt. And IL1 is 1 over L1 integral of V of t dt. That is the voltage there, right? So that voltage is in common. So L1 plus IL2, which has to be equal to my source, has to be equal to 1 over L1 times the integral of V of t dt plus 1 over L2 integral of V of t dt. Since those are in common, we can go 1 over L1 plus 1 over L2 times the integral of V of t dt. For equivalency, my one inductor has to be the same, give me the same results. So IS is equal to 1 over L equivalent, the integral of VT dt. So 1 over L equivalent is equal to 1 over L1 plus 1 over L2. L equivalent is equal to 1 over L1 plus 1 over L2 raised to the minus 1. Or if you don't like that, you can do product over sum, right? Isn't that what we do with resistors in parallel with each other? It's the same exact concept for resistors and inductors. But now, hopefully what you see is the actual derivation of how that is done. Nothing up my hands, no tricks or anything like that. It's just making it so that you have hopefully a better understanding. Okay, so we showed that, and we showed that. But over the weekend, just try practicing. See if you can do the capacitors in the series and in parallel. See if you get what the value is. And then on Tuesday, we'll just start doing the review. We might finish because I think there's only 4 slides left for this one. So we might do a couple of those, but for the most part, that's it. So any questions? TV land or in-person land?
What time is the exam on? Is that going to be during the lab?
During lab.
Okay.
So it'll be the same as the lab time. So if you want to do the exam online, that's fine. You'll just have to let me know. I'll put up some details on Brightspace when I get back to my office.
Haha. Emailing you now.
Yep. All right, any questions? All right, y'all. Have a great day. What amount of time is the test expected to take? I typically write the test so you can do it in around an hour, but I give you the full lab time to go ahead and do the test. Just to give you no time pressure.
Cool beans. Thank you, Paul. It was really good to explain the capacitor inductor again.
Yeah, anytime. I always like it because it really helps solidify our understanding. So that's a good thing. I think.
It did. We went over it in ECE324, but it's good to kind of brush up on this stuff, you know?
Yeah. A lot of reviews still, so.
No, that's great. Practice is good.
Yes. All right, guys. I will talk to you next week. Take care, everyone.
Thank you, Paul.
Thank you very much, Paul.
Thank you. Take care. Thank you.